Hi there. So what we're going to do now is start our final chapter for this particular course. And this chapter is super fun. It's on polynomial and rational functions. So we're only going to be covering about 4 or 5 sections in this chapter. And what we're going to do is we're first going to start out discussing what power functions and polynomials are. All right, so to start, I will tell you that a power function is a function of the form y or f of x is equal to k times x to the power of p, not to be confused with our exponential functions. Okay, recall the exponential functions that we had, our variable was in our exponent and our base was the constant. Okay, we're back to polynomial functions. Okay, so P is called our power and K is a constant or it's a coefficient, however you want to term it. It's a real number. Okay, now when we're talking about power functions, unlike polynomials, we have no restriction on the value of P. Okay, so what I want us to do before we delve into these power functions and then get to polynomials is just be sure that we're comfortable with looking at our power functions. Okay, so for example, I could say that our identity function, we've studied lines. Again, this is a line with slope 1, y-intercept of 0. But I claim this is a power function. In this form, I claim that our value of k is 1 and our value of p is 1. Okay, again, we wouldn't write it this way, but we could say it's 1 times x to the first power. Okay. Another example, y equals the square root of x is an example of a power function. We can rewrite that as x to the 1/2 power. And then in this case, we would say, well, our number out in front, we don't have one. Therefore, by default, it's 1. And our power, p, is 1/2. All right, a couple more. What if I tell you y equals 5 is a power function? Okay, well, how would we write this as k times x raised to some power? I claim I can write that as 5 times x to the 0 power because we know that anything raised to the 0 power is 1. So in this case, our k is 5 and our p is 0. And finally, how about, well, let's do a couple more just to be sure we're good. What if I write y equals 1 over 7x? It's not a very pretty looking function, but this certainly is a power function. First thing I'm going to do is rewrite this step by step as 1 over 7 times 1 over x. Again, when you multiply two fractions, you multiply your numerators and you multiply your denominators. But notice we want this as x raised to some power, and we have an x in our denominator. So how do we bring that up to our numerator? Remember, you change the sign of your exponent. By default, this is 1. So I can say this is 1/7 x to the negative first power. All right, so what we can say then is our k value is 1/7 and our p is -1. All right, well, one more just to get us going. What if I have something super ugly like this? Y equals pi over 3 times the 5th root of x. Well, again, why don't we separate out our constant from our variable part? We can write this as pi over 3. times 1 over the 5th root of x, which is pi over 3 times 1 over x to the 1/5 power. We know the 5th root is 1/5 power. And finally, we want to have our x up here, so that makes our exponent negative. So in this case, k is pi over 3, and p is negative 1/5. Now, fortunately, we're not going to have to play with things like this, but it is really important to be able to manipulate our functions in this way to identify what our coefficients are, as well as our exponents. All right, so some things that I want to mention to keep laying some groundwork is I want to note that our graphs for these functions are really, really cool, okay? And I want to start pointing out some patterns here that we're going to establish and grow from. So for example, when I have y equals x, we know that this is the equation of a line with slope 1 and y-intercept 0. And I could say, well, y equals negative x. In other words, I'm just going to make it a negative coefficient. Just looks like this. Okay. Other power functions. Notice this is a power function where our power is 1. I can look at y equals x squared. This is another one of those toolkit functions that we started out with. We'll be examining this in much greater detail in the next section. But we know that this is a parabola that looks like this. And if I wanted to graph negative x squared, well, we know that when we throw a negative in front of our function, that's a reflection about our x-axis. So that would look like this. All right, 2 more that I want to show you just to start establishing a pattern. So we have a power function with the power of 1, a power function with the power of 2, and now we're going to do a power of 3. This was another one of our toolkit functions. You may recall I call this our John Travolta function. That's our y equals x cubed. And if we wanted to look at negative x cubed again, that just takes our graph and reflects it about our x-axis. So this would reflect here, and this portion would reflect up here. Finally, we can look at y equals x to the 4th. That looks very much like our quadratic here, but it's flatter at first, and then it really shoots up. And again, to follow what we've been doing, we can also look at what happens when we take a negative of it. Okay, again, we've played with these graphs throughout this course. And if you're unsure, you can always make those little XYT tables. But what I want to talk about in particular is the effect that our exponent has on these power functions. Notice here, both of our exponents are odd, and here, both of our exponents are even. Okay, and there's something common going on with each of these graphs. In fact, what I'm going to tell you is that the exponent, or our power, has a big effect on our graph. Essentially, what it does is it tells us about the end behavior, or what we call the long run behavior. Okay, what do I mean by end behavior or long run behavior? Essentially, what happens as x gets really big or really small? And the way we say is what happens as x goes to positive or negative infinity. Okay. And what we're going to see with these power functions is that our functions are either going to shoot up or shoot down to positive and negative infinity. And in particular, what we see is that when we have an even exponent, notice both of our arms either go up to positive infinity or both of our arms go down to negative infinity. What was the difference? Notice here they both go to positive infinity when the number in front of x is positive, and when our coefficient is negative, they both go to negative infinity. So when you have an even exponent, okay, a lot of funky things can happen in the middle, but our long run behavior says that if the coefficient is positive, our function's going to shoot up to positive infinity as x gets really large and as x gets really small, or it's going to shoot down to negative infinity if our coefficient is negative. The other thing we can summarize is that when we have an odd exponent, notice one arm goes up and one arm goes down, right? And what we can conclude there is that when our coefficient is positive, as x gets large, our function's going to shoot up to positive infinity. And as x gets small, it's going to shoot down to negative infinity. And we have the opposite happening when we have a negative coefficient. Okay. Now, do you need to memorize these? Absolutely not, but these patterns are essential, okay? And I'll keep coming back to this, okay? This gives us big, big clues as to what happens with our functions. Okay, so that's what we need to say about our power functions. We don't get very deep into those. But what I will say is from those, we can grow into polynomials. And polynomials are the sum of power functions, but very particular type of power functions. They're the sum of power functions that have no fractional or negative exponents. Okay, now we can write out the definition of what a polynomial function looks like. Essentially, what we do is we take a bunch of different power functions. So here's one, and I add on another, and I can keep adding them on as long as I want. These a values with these subscripts are coefficients. They're real numbers. And we tend to write these with the highest exponent first and then in decreasing order. And what I'll tell you is that the highest power on x is called the degree of the polynomial. Okay? The term with the highest power is called the leading term. And that a value, in other words, the number in front of that x value, is called the leading coefficient. These are not terms you need to memorize, but you need to be aware of them because they come up so frequently. Okay, so for example, I'm just randomly writing this polynomial down. Okay, I claim that this is a polynomial. This is the sum of three different power functions. Okay, what I would tell you is that this polynomial has a degree of 3 because that's our largest exponent. Our leading term is this term, 7x cubed. And using the definitions above, our leading coefficient is 7. Okay, now what we're going to do in this chapter is gain the skills so that we can graph these guys. And that is so super fun. Now, already from what we've talked about in terms of the long run behavior, we don't know what happens in here, but notice this is an odd degree and the coefficient in front of it is positive. So whatever else happens in here, I know as x gets big, my function's going to shoot up to positive infinity. And as x gets infinitely small, my function is going to shoot down to negative infinity. All right. So what I want to do right now is just summarize and say that the long run behavior of a polynomial is completely determined by the leading term. The degree tells us what our exponent is, and therefore if we're going to be going up or down, as well as the sign of our leading coefficient. Now, that tells us about the long run behavior. And that's a really good check mechanism that we're going to be coming back to. But what I want to say is a lot can happen in the short run. And so what we're going to do now is we're going to start looking at the short run behavior because that needs to be analyzed. Now, in order to do that, we're going to come back and talk about some terms that we've used before, and we're going to apply them to this context. So one term that we have is called our vertical intercept or our y-intercept. Okay. And recall that's where, if we're looking at a picture, the graph touches or crosses our y-axis. And it always has the form 0y because we know that no matter where we're at on our y-axis, our value of x is 0. Now, when we have an equation of a function and we want to find our vertical intercept, recall we know how to do that as well. We set x equal to 0, and then we solve for y. Now, the other thing that we have discussed is called our horizontal intercept or our x-intercepts. And similarly, we saw that this is where the graph touches or crosses our x-axis. We know that no matter where we are on our x-axis, our ordered pair has this form. And we've also seen that in order to find our horizontal or x-intercept, what we do is we set y equal to 0 and solve for x. My friends, when we were dealing with lines, we could do this. When we take this into other sorts of functions, it becomes a very non-trivial process. Okay, so what I want us to do now is play with this idea. Okay, So we're going to really hone in on these horizontal intercepts, okay? Our y-intercept we're going to find is like our sweet spot. We definitely can find this, and it's not too much trouble because when we put in x equals 0, things just tend to cancel, okay? Our horizontal intercept actually has some aliases, okay? They can be called roots or zeros, okay? Recall, if we have y equals f of x, and we want to find that horizontal intercept, we set y equal to 0. In other words, what we're doing is we're setting our function equal to 0, okay? And what we want to do is find those values of x, okay? So what I want to do is first start by drawing a graph. Okay. Now, I don't know what this function is, but I'm going to tell you by the way I drew it. I know that it's an even degree and that my leading coefficient is negative. How do I know that? Again, because both arms are going down. Okay. And we saw that with an even degree, both arms go up or both arms go down. But in this case, since both arms went down, we know our leading coefficient is negative. Now, graphically, I have 3 x-intercepts here. Different things are happening at each of these x-intercepts. Notice we always look at our graph going from left to right. So here we're crossing our x-axis. Here we're crossing our x-axis. Notice we're going from negative to positive. Here we're going from positive to negative. And notice here, we're not crossing our axis, but we're bouncing off of it. And again, we have our one y-intercept here. You can't have more than one y-intercept because otherwise you don't have a function. Okay. So what I want us to do now is consider 3 graphs. Okay. And we're going to hone in on these intercepts, roots, zeros, etc. Okay. So what I want us to do now is consider the following graphs. Okay, there's one function. And suppose this is another one. And suppose here we have a third one. Now, I claim that all 3 of these graphs could represent 4th degree polynomials. Okay. Now, what am I trying to get at here? Well, what I'm trying to get at here is notice in all 3 of these graphs, the end or long run behavior is the same. But the short run behavior, in other words, what happens within this area here is quite different. So what we're going to do now is hone in and analyze this short run behavior. Now, what I'm going to tell you are a couple rules of thumb that we have that will also be very helpful as when we discuss, for example, the long run behavior. Okay. So what I'm going to tell you is that a polynomial of degree n, in other words, that's our largest exponent, has at most n horizontal or x-intercepts. And a polynomial of degree n has at most n minus 1, what we call turning points. And turning points is where our function or our graph goes from increasing to decreasing or decreasing to increasing. Now, this is really, really powerful, okay? What it says is that when we're dealing with polynomials, you're not going to have really funky stuff like this. It's not going to go increase, decrease, increase, decrease. That's just not what happens, okay? Now, one in particular that I want to point out, we've graphed many times, is y equals x cubed. This is a degree 3 polynomial. But what I want to mention is notice we have only one intercept, okay? And this follows because when we're talking about a degree 3 polynomial, what this says is we can have at most 3 intercepts, okay? In this case, we just have one. The other thing is, notice here, we have no turning points. This is increasing everywhere, okay? So that's what we mean by at most. So for example, if we look at y equals x squared, what we're saying is we can have at most 2 intercepts. That's the most we can have. And here's an example with 2 intercepts. Here's an example where we just have 1 intercept. And I could also have a graph down here that has no intercepts. This never touches or crosses my axis. But notice in each of these cases, we have exactly one turning point. It goes from decreasing to increasing or increasing to decreasing. Okay, don't worry, we're going to be keeping all of these things in mind as we go. Now, one other thing that I want to remind you of is the following. We have our zero property. And what that zero property tells us is if you multiply 2 numbers and get 0, then either the first one is 0, the second one is 0, or both are 0. Okay, this works with multiplication, and this is really, really key here. Okay, so for example, if I have something like x minus 2 times x plus 3 equal to 0, I'm multiplying 2 terms and I'm getting 0. What this 0 property tells us is then either the first thing is 0 or the second thing is 0. Well, what makes this first term equal to 0? We can certainly solve for x by adding 2 to both sides. We get 2. And we can certainly figure out what makes this equal to 0 by subtracting 3 from both sides, or we get x to be -3. In a situation like this, notice, if this was our function and we set it equal to 0, we found what we call our zeros, our x-intercepts, or our roots. And what I want you to note is that in general, if x minus k is a factor of a polynomial, then x equals k is a 0. Because if it's a factor, that means you're multiplying this by something else to get 0. And by setting this equal to 0 and solving for x, you get k. All right. So seemingly I'm going somewhere with this. Well, let's just practice this idea with our intercepts. Suppose I have a function that looks like this. Okay. And suppose I want us to find the horizontal and vertical intercepts. Okay. Well, my vertical one is my favorite one to find because what do? We set x equal to 0 and we solve for y. Okay. So if I plug in x equals 0 here, I have 3 times 0 plus 1 times 0 minus 4 times 0 plus 5. I have 3 places to plug in x equals 0, which is 3. Well, 0 plus 1 is 1. 0 minus 4 is -4. 0 plus 5 is 5. And we are going to get -60. 3 times -4 times 5. So my vertical intercept is at the ordered pair 0, -60. Okay. Now, to find our horizontal intercepts, what we do is we set our function equal to 0. Well, if I set this whole shebang equal to 0, I can now use my 0 property. Notice I'm multiplying 4 things together to get 0. And my 0 property says, well, then at least one of them must be equal to 0. So we can start out by saying, well, either the first one is 0, or the second one is 0, or the third term is 0, or the fourth term is 0. Well, this is nonsense. The 3 is just not going to contribute to that. But we can solve each of these for x and say, well, -1, +4, and -5. In other words, we have -1, 0, 4, 0, and -5, 0. Now, what's super cool is we haven't done anything with graphing this function, but I claim I can say a lot of things about it. Okay. First off, we could multiply this out. I claim that if you do notice we have x, that's going to give us x cubed. If you don't believe me, I suggest that you use the distributive property and do this. But just from everything that we've done so far, we can say, well, this is a 3rd degree polynomial. My leading coefficient is positive. So I know in the end, one arm is going to go up and one arm is going to go down. Furthermore, I know that this crosses my vertical axis at -60. And I know it crosses my horizontal axis at -1, 4, and -5. Okay. Now, I also know that if this is a 3rd degree polynomial, notice we have at most 3 intercepts. And from what we talked about back here, we have at most 2 turning points. In other words, where the function changes direction. Okay. Well, again, since our leading coefficient is positive and this is a 3rd degree, I already know that something like this is going to happen. Again, there's no funky things going up, down, up, down, up, down. I know that I've got to come and hit this point. I know I've got to come and hit this point. And then I know that I've got to come back down. Now, I don't know how high it gets here. We need more detail. But again, I know that I'm going to have at most 2 turning points, and this arm has to go up and this arm has to go down. All right, let's just practice finding the intercepts with another example. Suppose now I want us to find the vertical and horizontal intercepts of this. All right. Well, my vertical intercept is cute. We plug in x equals 0. Notice if I do that already, I already know what's going to happen. I have a 0 here. No matter what happens, 0 times whatever else these things are, we're going to get 0. Notice this is also going to be one of my horizontal intercepts as well. Okay, so for my horizontal, notice what we do is we set our function equal to 0. Well, in this case, this is my function, and I'm going to set it equal to 0. Well, we can only multiply things together to get 0 if at least one of these is 0. Notice that means either my first term is 0, my second term is 0, or my third term is 0. We can solve each of these for x. Here you would just multiply or divide by -1. That gives us x equals 0, which jives with that. Here what I would do is I would add x to both sides, and I would get x to be 4. So another 0 or horizontal intercept is at the ordered pair 4, 0. And here, first I would subtract 3 from both sides and then divide by 4. So my final horizontal intercept here is -3/4, 0. All right. Well, that concludes section 3.1.